third speaker, this is Staffan Qvist from the Consulting Limited, Sweden. Staffan Qvist is an independent energy researcher and consultant. He holds a Ph.D. in nuclear engineering from University of California, Berkeley. At Berkeley, Staffan invented the autonomous reactivity control system for passive safety, a new generation of nuclear reactor. Please, the floor is yours.
Thank you very much. Good morning, everyone, and thank you to the organizers for inviting me to speak. Usually when I'm here to speak about really detailed technical issues. It's my pleasure today to take a step back and look at the broader picture. And I would say we've had 3 days of fantastic information sharing. So at the third day, it gets harder and harder to share new, interesting information, but I'll give it a shot. So this conference is about the role of nuclear power in combating climate change. And I co-authored a book, not specifically focused on that. It's the book up here. It's called A Bright Future, but it does go through what has been successful and what hasn't been successful so far in efforts to combat climate change. And obviously nuclear plays a role in any such book. So anyone who's ever wrote a book is supposed to plug it when you come to speak. So I don't have any with me, but you can find it in great bookstores everywhere. And we have, I guess, 6 languages now. So what we do in the book, I can't go through all of it, but the main thing is the approach to solving problems that you typically employ in your life. And the most effective way to try to solve a new problem that you face is almost always to go look if anyone else already solved the same problem. And if you can find someone who solved the same problem, go ask them, how did you do this? How long did it take? How much did it cost? And is there any way I can do the same thing? So if your problem, and I want to find new, I recommend everyone to go to YouTube and just type in how to and nothing else and just search that, and you will find people explaining literally everything in the universe to you in very, very nice ways. So if you want to make slime without glue in 10 different ways, some madman has gone through that. And if you want to make fluffy Japanese pancakes, install an elevator in your living room that has 13 million views. But we can employ basically, and that's what we're doing in the book, the same methodology to how do we solve at least part of the climate change problem, which is decarbonizing electricity. So there hasn't been any decarbonization plan that doesn't expand clean electricity and electrifies other sectors. So electricity really is the key. And we have the equivalent to these YouTube videos now. It used to be boring Excel spreadsheets or even physical spreadsheets. Now we have something called electricity map. So we know how we've done. We know graphically how the world has done on this topic so far. So this, what you're seeing here, this map is from electricitymap.org. It shows you all of the regions of the world that they could find that reports hourly data on how they produce electricity. And then they've just color-coded how dirty or clean that electricity production is. So if you have a country, a region here that's green, it doesn't emit a lot of greenhouse gases. If it's brown, it's dirty. And if it gets darker brown, it's even dirtier. And so a bunch of this data is actually hourly. Then I've overlaid some countries at just a static level just to show more of the world. So China and Russia here, for instance, will not fluctuate. But actually, what you can do is animate every single hour of last year, for instance, and see, was the electricity produced clean or was it dirty? And you can see here really every hour of the year for all these regions, which is quite fantastic. And what you see is quite interesting. So what we are looking for is how this problem was solved. And was it solved somewhere, and how was it solved? So what we are interested in is basically the areas that are always green. Green 24/7. How did they become green 24/7? Could the rest of the countries do the same thing and the whole world will be green 24/7, at least for electricity production? And what we find is there's 2 basic ways to do this, so far at least. Most of the green areas here are green because of luck, because of geographic luck. They have large flowing rivers going through their countries, or they have geothermal energy close to the ground that they can tap for geothermal power. And so if you see the the areas in South America, so parts of Brazil, or New Zealand over here, Tasmania, Iceland, parts of the north of Canada, these are all hydroelectric and hydroelectric plus geothermal systems. So this is geographic luck that these regions are green. Costa Rica is another good example of hydro and geothermal. It's wonderful, but no one can copy that. It's not a recipe for anyone else to follow, because the other nations didn't happen to have that luck. What we have to be inspired by, and what we focus the book on, is the few regions, basically 3 or 4 regions of the world, that are always green and did it in a way that wasn't just based on luck so far. And those regions are my home country, Sweden here. Norway, that's next to us, is just abundantly lucky in everything, and they have abundant hydropower too, so we can't be inspired by them. And then there's France and Ontario, and Switzerland, if we're really generous to Switzerland. These are the 4 places that done this in a way that's not just luck-based. And if we zoom into Europe, we can look at the same thing, and then we can focus on the 2 green lights on the map in Europe, because Europe has the best data collection for this. You see, and this is quite interesting, you see Norway always green, hydro, Sweden always green, and France always green. And then you have countries like Denmark and Germany who have employed a different strategy. You see this purple here is wind. So this is the wind power coming in, so gusts of wind. And when the wind comes in, you can see Germany and Denmark turn green. You can see Denmark turn so green that they produce all the power they need and even export green electricity to other countries. But what you see, which is interesting, is then they turn back into brown. Denmark not so much, because they can buy hydro from Norway, but Germany is kind of a blinking light going from green or yellowish to darker brown, and just oscillates like that. So far that hasn't been a good, effective strategy to do this. The countries that have succeeded have all done it in the exact same way, more or less, variations on the same theme. A strong, renewable electricity sector paired with nuclear. So that's what has worked so far. It doesn't prove that's the only way or even the best way to do it in the future, but it's what has worked, and that's what the data shows. So another way to look at the same data is to graph out. So here on the x-axis we have the amount of carbon dioxide emitted per kilowatt hour, and you have, I've grouped this into 3 different approaches to decarbonizing electricity. The first one is what I call a balanced approach, which is renewables plus nuclear. The second one is Denmark. It's got its own grouping here because they're relying on other people's clean energy and their own dirty energy and some of their own clean energy. And then the third grouping is what is the most popular approach today to decarbonization, which is variable renewables plus gas. And so if we look at the last 90 days, this is what happens. The first group is very boring on a graph because nothing happens, it's always clean. And the more you go down the path here, the more you start bouncing between clean and dirty. But what the problem they're facing is these blue dots here, that's the average. And they have a very hard time getting, it's easy to go down a bit here to reduce your average. But when you're bouncing up and down in between clean and dirty, you never really get here. That's really difficult. You can get down this path by doing this, but the jump down to here requires something else, and that's what we can see from data. So this might look insane to a lot of you having discussed this, but this is my perception of how this discussion is happening, at least my myopic European perception. We have what I call dead arguments. They're dead because no one in this room, apart from maybe Jerry Thomas, needs to engage on this. We have credible scientific, objective, competent scientific organizations that states these things, and we can just reference them. So IPCC obviously says nuclear is low carbon. No one here needs to say anything, but if you want to challenge the IPCC, go ahead and do that. Same for safety. There are tired arguments, which is there's no solution to waste. Finland is now building their licensed waste repository, so that has a shelf life of maybe a few years, but then that's going to be in operation. And it's less catchy to say there's no solution than to say there's no solution apart from the licensed and functionally operating repository in Finland. That's not a slogan that you want to put on an anti-nuclear campaign or whatever. But what we have now to really discuss in a serious policy debate is nuclear too slow and it's cost effective. And I've used far too much of my time already to be able to even go through what I was going to say about that. So I'm gonna jump through. Is nuclear too slow? Some of you might have seen this. We're producing electricity as dirty today as we were in 1990. We haven't done anything to the average emissions intensity of electricity. We're producing more, so we're emitting more. What we can do is look at how this trajectory would bend in given various strategies. So if we build no new low carbon, obviously this will increase a bit. But where would it go if we employed strategies that have been done historically? And the most interesting one, I think, is the one of Germany, which is really 100% renewable prototype, let's say, proof of concept. If we apply the actual Energiewende data, we don't bend this at all. So if everyone would follow Germany's lead and build the way Germany does, normalized by economy, we wouldn't do anything. If we only do the clean energy ad and forget that they shut down nuclear, we still don't do much. If you just take the best years, we still don't do much. And so that's not a bright future, that example. But what we have in the book and in the real world and in the data is examples of the world building clean energy fast enough to actually decarbonize global electricity. And I've just graphed out Sweden and France here in the same way. If the world did what Sweden and France did, normalized by the economy, we would actually decarbonize what we think is electricity, at least, in a fairly good time frame. Obviously, then you have, total energy is much bigger than that. So what does a failed climate plan look like? And this is starting to seep out, I guess. There's been a good PR effort by Germany to try to hide this, and you can graph this out in different ways. What the climate cares about is emissions, not how much nuclear power plants you build, or wind farms, or solar farms, or whatever. And if you look, so I like to graph it out this way. This is how much Germany burns in terms of fossil fuels and forests to produce electricity. And since 2000, that's up 4%. So that's by definition a failed climate plan. They might say we have more percentage points of generation that's renewable, but the climate doesn't really care about that. So this is going to be very rushed now, explaining reality, facing reality. So what I'm trying to do and what I think we need to do is to explain reality in a similar way to this and explain what has been discussed a lot in this conference already, so I can't add much to this, but to really get people and policymakers to understand that you pay for an entire system. So you pay in some way for the entire system, through taxes, through electricity charges, through tariffs, whatever. Intermediate points towards decarbonization are not the easiest way to get an incremental decarbonization happening will not be a point on the way to full decarbonization. That's a tricky point to explain. Coal to gas shifting, for instance, is a typical example of this. You can reduce your emissions by half by switching from coal to gas, but then you're stuck at gas. So the switch to gas is not a way towards full decarbonization. What we found in the most detailed modeling that we've done is that system costs are always lower when you do long-term operation of existing nuclear power plants. They're also lower with new plants if you have strict decarbonization targets. So we did a very, very detailed study, the most detailed studies ever done for Sweden, and that's not so interesting for the world because it's a small market. But it is interesting as an outlier case, because Sweden is maybe the easiest country in the world to go fully 100% renewable. It's got a huge hydroelectric sector with massive reservoirs. It builds some of the cheapest onshore wind in the world. It's got massive areas to do so. And so if we see nuclear popping up in the lowest cost system in Sweden, we'll see it popping up everywhere. And what we see is, at least in every single scenario we can throw at this model, long-term operation of all the existing nuclear power plants are a part of the lowest cost system. And this is embracing the most optimistic cost projection scenarios for everything else, for solar, for wind, for batteries, for hydrogen, for what you want. The LTO is always there. For new nuclear, well, the LTO is always there in the model. In the real world, and this is where we're failing, LTO isn't happening, and Sweden is actually shutting down 2 currently profitable working reactors. And so we are failing. No one is disputing that this is true. No one can scientifically dispute that the LTO would be system cost optimal. In the real world, the way the market's set up, these reactors are shutting down. So we need to do something about that. For new nuclear, it's more complicated. I would love to discuss all of this, but my time management skills for doing this presentation is bad enough that I can't. But please come up to me and talk and email me, and we'll discuss this. What I wanted to say basically is let's collaborate on these things. Technology neutral systems modeling is critical to explaining why nuclear should have a role in the future low carbon system. For this to have policy relevance, this needs to be done in detail. It needs to be done on the political level where decisions are made, so usually a national basis. If you make a generic study saying nuclear is good for the system cost, everyone who's skeptical will say, well, that doesn't apply in our country. So what we found is we have to make a detailed study for each region, or usually nation or state within a nation. We're doing this in Sweden now with the CBI, so the Confederation of Private Enterprise. It's not a nuclear study, it's just what is the cheapest way to achieve climate targets. And once you do it technology neutral, you include nuclear. We're going to do the same thing in Poland very soon. And I think we should all collaborate in trying to get this done everywhere. There's certainly no lack of 100% renewable system studies. There is a lack of the technology neutral equivalents. And then, once we've explained this, the logic behind this, what's really required is the really boring part for an engineer, is to design a market that actually makes this happen. So we can calculate what the lowest cost system would look like, but current market setup in the what we call liberalized electricity markets will never build that system. And so we need to collaborate and propose specific policies that would likely make that happen. If we don't, it's not going to come from the heavens. Someone needs to propose specific policies. So the UK is doing that with the regulated asset base. We need to maybe adapt that to all other countries or come up with something else and, you know, figure out how we design the markets to actually make the lowest cost system come to life. So that's the book again. That's my email address. Please find me after. Let's discuss. Let's collaborate. Thank you very much.